Good afternoon. Thanks for coming and listening to my talk. The title of my talk is Knowledge Engineering for COVID-19 Recognition. This talk is for ICCKE 2022 at Iran. As can be seen in this slide, I'm currently working as a professor in Department of Informatics, University of Leicester. I'm the fellow of the IET, fellow of EAI, senior member of IEEE, senior member of ACM. I was also awarded the highly cited researcher by Clary at Yale's 2019 and 2020. Currently, I supervise 12 PhD students as first supervisors and another 5 PhD students as second supervisors. My lab has 22 visiting scholars, and currently you can see my H index is 74 in Google Scholar. This slide shows the outline of this talk. There are two different diagnosis methods. The first is the reverse real-time PCR method. This is sometimes called a viral test. And we have some imaging methods. There are 3 commonly available imaging methods, like here the bottom left, the chest X-ray, and also on the top right, the chest CT, and finally the chest ultrasound, shown in the bottom right corner. This slide shows the real-time reverse transcription polymerase chain reaction. It can be shortened as the RT-PCR. As you can see, the nurses need to insert a swab into the nasal passage. And you can see here, and the swab should be put at the end of the nasopharynx point. And in this case, the swab may stay still there for about several seconds, or at most 10 seconds. And the swab needs to rotate it and then pulled out to get a sample. There are 3 samples. We can say the nasopharyngeal swab, the nasal swab, or the sputum sample. There are 3 weak points of the RT-PCR method. First, the swab itself may be contaminated. As you can see, the scientist.com web page has reported the CDC lab contamination delayed the coronavirus testing. The second is that the variants may negatively affect the detection. Also, there's the scientist.com web page news reported the COV2E gene variant alters the analytical sensitivity. The third weak point is the high false negative rate. As we can see here, there's one paper from radiology reported in the 413 patients with negative RT-PCR results, 308 of them had a positive chest CT finding. Compared to the RT-PCR, the chest imaging, the CI, has those 3 advantages. First, we can see the CI can detect the lesions of lungs where biomarks will be observed to distinguish the COVID-19. So we will detail the biomarks in the following slides. The second advantage is the CI can immediately give decisions as soon as the imaging is complete. And for the RT-PCR, you may need to wait for hours or even days. Like me, when I stay in UK, I also ordered the test set, and I needed to receive the package from the post, and then after I checked, I will send it back, and then wait for a few days, and my mobile phone will receive the message. And the last is the report shows that the chest computed tomography, the CCT, can detect 97 of the COVID-19 infection. So you can see here, the paper was published in the radiology last year. The comparison of the three imaging methods are listed here. In the chest X-rays, the disadvantage is the poor soft tissue, and the chest X-ray only can generate 2D images. The chest 3D, it is much better. It can provide a 3D chest data, and particularly it has the finest resolution, and it is better to recognize extremely small nodules. And finally, for the chest ultrasound, it is operator dependent. So different operators will produce different outputs, and also the ultrasound needs high level of operation skills, and it's hard to keep the ultrasound probe at the same position during scanning. The dataset we used in our study included both the public dataset and the private dataset. The public dataset we use is called the SARS-CoV-2 CT scan dataset, downloaded from the kaggle.com. It is obtained from the public hospital of the government employees of São Paulo, Brazil. This public dataset contains 1,252 CT scans of COVID-19, and meanwhile, another 1,230 CT scans of non-COVID-19. Meanwhile, we also prepared a private dataset. So why do we need a private dataset? Because we think the public dataset is a bit easy to train our model. So we just use some simple deep neural networks, and the accuracy can arrive at 99%. We analyze the reason, and we find their pictures are all high quality. But in realistic situation, and the CT scan, sometimes they are influenced by noises. And another reason why we created a private dataset is we want to include some other chest infectious disease. Like here, we include 71 patients with secondary pulmonary tuberculosis, the SPT, and 69 patients with community-acquired pneumonia, the CAP. So we use the private dataset to check whether our model can identify the 4 categories. Here shows the samples of 4 categories. On the top left, we show a COVID-19, and we can see the GGO leading areas here. And on the top right, we can see the SPT, and again there are some chest lesions, which shows this is a secondary pulmonary tuberculosis. And the bottom left is what we call the community-acquired pneumonia. And again, we can see clearly the symptoms, the medical presentations here. And finally, on the bottom right, which is the healthy controls, and we can see clear there's no lesions, no symptoms on this chest CT picture. How do we do the labeling on all the chest CT images? We first invite 2 radiologists, and they are here, D1 and D2. Those 2 radiologists, they should have the chest diagnostic experience more than 10 years. And they will collectively read the CT images. And if their CT, their outputs are the same here, and the results will be the final results. And if there are some disagreement, like here says some difference, and we will invite a superior doctor. Here the superior doctors here is a D3. They will reach a consensus by the majority voting. The pre-processing is quite important because you can see on the left hand, the original image are stored in DICOM, and it's very large, like 1024 by 1024, and they are, although the images are grayscale, but you can still know that they are stored in RGB, like 3 color channels. So there are a lot of information redundancy. And what we can notice here is that there are the check-up bed, because the patient lies on the bed, and on the right there are rulers and also some text. Usually there are some text like the hospital information and the patient information in the chest CT images, but here for the privacy we choose an image. There's no text information, so we need to do some things to handle these things. First, what we do is that we will transfer the RGB to grayscale, and again the original image, although it's not there's no color information in the original image, but the picture are stored in RGB, so we will try to transfer it into a grayscale, and then we will do some histogram stretch, try to balance the contrast and to enhance the contrast to make it more clearer to radiologists to the machines. Then we will try to do some margin and text crop. Here I think this is not correct because we should also add the bed, the checkup bed. We will crop the bed. Maybe the bed is located in the bottom margins, and then we will do the resizing. And for the resizing, it depends on your situation. In some pre-trained models, you need to resize it to 224 or 227. And in some other cases, for example, some custom network developed from scratch, it depends on the input requirement of your own network. And finally, on the right hand, you can see this is the pre-processed images. The data harmonization and augmentation is also an important pre-processing. The harmonization means we will adjust the data to make harmonize across the different sites and scanners. Suppose we have many different CT scanning machines, and if we want to put it together into the same data set, we need to do this kind of harmonization, because the different scanners they may have the different parameters. Another important thing we need to be aware is what we call the augmentation. The augmentation is to due to the limited size of our data set, we may need to create fake images using the flipping, sharing, scaling, rotation, translation things. So the bottom image just shows from one raw image, we can create the share, create the scaling, create the rotation and translation, and there are many other things like the noise injection to make like hundreds or even thousands of new fake images for only one single raw image. Transfer learning is a novel idea compared to the traditional machine learning method. In the transfer learning, you need to take a network trained on a different domain for a different source task. And then what you need to do is simply adapt it for your domain and your target task. And the ultimate goal of the transfer learning is to develop a universal model that can be adapted to every different task. The second improvement using transfer learning is we have a new method called the deep CCT fusion via DCA, and which is abbreviated here DCA. And first, let's watch the left hand part. Suppose we have an input CCT images, and we first use an SAPNF method to choose the optimal pre-trained models. So the pre-trained models can be any candidate like a NextNet, GoogleNet, or DenseNet, and the algorithms will choose automatically. And after we obtain the best two pre-trained models, and we will use a method called L2TFL method to extract the learned features, FM1 and FM2. And finally, those two features will be sent to this box, the DCA, and we have some very complicated algorithms, procedures here. We will extract the between class scatter matrix and then to do some other steps. And finally, after the deep fusion, we will get the final feature GDCA. And this method, we tested our method on 4 categories. The first is the COVID-19, and the second is, I think, is the CAP, the community-acquired pneumonia. The third one is the secondary tuberculosis. And the last one is the healthy control. And we see here we have a Microsoft a micro average. The F1 score is as high as 97%, and also all the sensitivities, precision, and F1 score per class are above 96. So we can see our method is quite good. And besides, we compare our method with a lot of the different baseline, and we find our method achieves the best result. You can see here. And this paper was recently published in Information, and here is the volumes and the page numbers. So anyone who are interested, you can download, or you can search. You can Google the title, and there's the open access text and source code in ResearchGate. We have a fourth improvement based on transfer learning. Here we choose the DenseNet as the backbone model, and we used a new method called the optimization of transfer learning setting. On the left-hand side, you can see how the DenseNet will classify the chest images. The input is a chest CT images, and it will go through a convolutional layer, and we have some DenseNet block, and we have the transition layers, and after the DB1, TL1, and DB2, TL2, DB3, TL3, and DB4, and we will go through a gap plus the FCL plus softmax, and the prediction will output whether the input is a COVID-19 or it is a healthy control image. On the right-hand side, we see like the structure of the DenseNet 121, and particularly we expand one block, the DB1, here one layer deep view of this DB1 block, and we tested the 3 variants of the DenseNet, which we will show in the next slide. Here we tested the 4 different settings. The setting 1, setting 2, setting 3, and setting 4. In each setting, we break all the layers into 3 parts. The first is the floating layers, which the learning factor is set to 0, and the middle layers, where the learning factor is set to 1, and then the new layers, the learning factor is set to 10. So from the left to the right, the learning factor is from 0 to 1 to 10, which corresponds to the nerd learning, the slower learning, and the faster learning. And finally, we tested 3 different variants of DenseNet, the 121, the 169, and the 201. And the 3 variants times the 4 settings, so in total we tested 12 different combinations, and we find that the best is the 201 plus the setting 4. And these results was reported in the cognitive computation. The 5th model is we proposed an MFBC-NNC method for COVID-19. Here we first based on the biogeography-based optimization, and in our paper we proposed a new factor called the migration momentum factor, and we use this variable to control the migration speed. On the right side, we can see the flowchart of the proposed MF-BBO. Then we tested 3 pre-trained models, the LET5, VGG6, and the ResLET18. And we tested the CNN models without any optimization algorithms. And you can see the overall accuracy in this flowchart. Then we tested the average overall accuracy of 3 models with the ordinary BBO, and the average overall accuracy of the 3 models with the proposed MF-BBO. And finally, we can see the detailed confusion matrix using the MF-BBO. And here we show the results on the LET5, VGG6, and the ResLET8. We tested on the 3 classes, the COVID-19 class, the normal class, and the pneumonia class. So this paper is published in the Knowledge-Based Systems at 2021. 4 graph convolutional networks are introduced. We will introduce in the following slides the ResGNet-C, the CGNet, FGCNet, and the NAGNN. Now let us discuss the motivation of using graph. From the top image, we can think like each image will be considered as a node. And when we construct the graph, it means we want to learn the relation-aware representations. So using the graph convolutional neural network, the inspiration is to not only learn the image level representation, but also learn the representation between different images. And why are we using it? Because we expect the AI system using the graph will generate a more accurate results if we're considering the relationship among the input images. So here it shows how the graph is constructed. The first is we use the k-means clustering to generate the cluster centroids from the batch of our test images. And then we use the k-nearest neighbors algorithms, the KNN, to generate the adjacency matrix. Here on the left, we choose the feature domains. The feature domains, where we can see here each node represents a test image. And we will use the cosine distance to calculate the distances among every 2 images. Here, that means every 2 nodes. And if the node I belongs to the KNN of the node J, or the node J belongs to the KNN of the node I, we will give the value of 1 to the corresponding the ith row and the jth column. And otherwise, if I does not locate in the k nearest neighbors of node J and vice versa, then we will give a 0 on that ith row and jth column. The ResGNet is a fusion of the ResNet 101 with a graph neural network. We can see here the main branch. The main line is an input, and then to the ResNet, and finally to a fully collected layer with 2 neurons, because in this network we only need to recognize COVID-19 from the healthy subjects. And if we want to add the graph, you can see here, add the graph as a side branch, and the features from the graph and the features from the conventional convolutional neural network will be fused by this asterisk. The asterisk in the circle means it's a kind of production of the adjacency matrix of the graphs and the features from the CNN. And what are the results? We can find that the ResGNet can get a sensitivity of more than 97.33, and meanwhile the specificity is about 95.91, and also you can see the F1 and the precision, the accuracy are all above 96%. The result was accepted in neural computing, and it will be published soon. The second AI model we proposed is called the CGNet. On the left of this slide, you can see in total we have like 10 steps. And at the step 1 till 3, we can see here this is a link to the CNN features. The CNN features obtained from 1,000 dimensional fully collected layers. And below we can see here we will come to the graph construction. The graph construction is associated to the step 5 and 6, which we will use the features to build the graphs in each batch of the features. And finally, we have a GNet. This GNet, the graph neural network, we can see here is associated to our step 8 till and 9. So this CGNet you can think is like a kind of the two-phase neural network. At the earlier phase, we will use CNN to extract features, and at the later phase, we will use the graph neural network to train the graph. And this kind of graph is a kind of relationship from each batch of the features. And you may ask, can we train the CNN features and the GNN features together? That's our next slide we'll discuss. The FGCNet has a similar idea of the previous ResGNet-C. Here, suppose we have a dataset contains the COVID-19 and healthy subjects. We first using a self-developed CNN to extract the CNN features. Yeah, here it shows the CNN features. And here we use like in total like 17 blocks to extract the CNN features. The CNN features will be passed through the K-means clustering method to calculate the centroid. Here we can see the centroid, and then again we use the K-nearest neighbors to help to construct a graph. So we can hear the graph will represent the cluster centroid correlations, and we will the novelty is that we will build a graph convolutional network, and in that paper we built a two-layer graph convolutional network, and after training we will extract the relation-aware representation features here, and on the left is what we call the individual image level representation. Both two groups of features will be multiplied element-wise by a deep feature filling strategy, and then the multiplication result will passed into linear projection and followed by a softmax, and finally is a cross entropy loss here. The left picture shows the comparison of our FGCNet against all the state-of-the-art method. Here we just using like in total 7 indicators. The definition of all those 7 indicators can be found in the reference. And on the right, we use some explainability like explainable AI method to give the heat map of how the AI reads the chest CT images. We can find here the left there's a circle here. There's a red circle shows how the radiologist will delineate the lesions of the COVID-19 patient, and on the right, similarly we can see that our AI model can locate and find the exact position, the precise positions of the lesions of the COVID-19, which demonstrate the effectiveness of our FGCNet model. So this slide we will introduce the NAGNN. The full name is Neighboring Aware Graph Neural Network. On the left side, we can show there's an overview of our model. Roughly speaking, we first use the transfer learning, and then the extracted features are sent to a neighboring aware representation block. And finally, we have a GRVFL training to output the result. On the right, we showed the 3 contributions. In our paper, we proposed a novel image level representation learning algorithms. This is used to find the optimal backbone model. We proposed a novel universal neighboring aware representation called the NAR, and the schematic of the NAR is shown in the top right side. And finally, we proposed a novel graph random vector functional link. On the left side, we show some post-hoc attention map for both the private CT images and the public CT images. On the right, you can see like we have two screenshots from the University of Leicester and the UK Today News. So actually, this research output was reported and covered by over 70 presses. We also, like, let's say, the Media Express, the Eureka Alert, the India Times, have already covered this news. This slide shows the idea of fusion of chest X-ray and chest CT. So we all know that the chest CT is three-dimensional. So here we only use one typical slice, but in our algorithm, we use the whole 3D chest CT. And the picture B shows one slice of the chest X-ray image. And our idea is that we develop two, let's say, like the multiple input. That means we have two input, and one input will receive the chest CT image, and another input will receive the chest X-ray image. We hope we can develop an end-to-end model that can fuse the features of both sources of images, and we would like to check whether this kind of fusion can obtain better performance. On this slide, we define two models. The first model is what we call the multiple input deep convolutional attention network, which is abbreviated as the MIDCAN. And the opposite is the single input, which we will call the SIDCAN. So after fusion, we have the images from both the chest CT and from the chest X-ray. And those, we can see here, those two sources of images, they will go through some layers, and those layers will be flattened and concatenated together and sent to two fully connected layers. So we call it, this is a MIDCAN, the multi-input. And on the other side, we have the SIDCAN. That means only use the chest CT, and another SIDCAN that use the chest X-ray. So we will carry out some experiments to check whether the chest CT and the chest X-ray, their fusion, their combination can achieve better performance than just using those imaging modalities individually. On the left side, we can see the AUC comparison of the proposed MIDCAN. The AUC value is 0.98. Compared to using the chest CT only, the AUC is 0.96. And compared to using the chest X-ray only, the AUC value is 0.95. On the right, we see the manual delineation and heat map result from the same patient. And the red circles is how the radiologist they circle it before our experiment. And on the right side, you can see which is the heat map generated by the MIDCAN model. As we can see, the heat map generated by the MIDCAN matches the manual delineation from our radiologist. Now we come to the task of the weekly supervised learning. First, we need to understand what is the weak supervision. It means we may use the noisy or limited or imprecise sources to provide the supervision signals for labeling. And what are the causes for the low quality annotations? Please see the left side image. There are several common causes, like the cheap annotation from non-experts, or the heuristically identifying patterns. Also, there are some cases like the batch annotation on the cluster of the data, or using noisy prediction from pre-trained models. And so in our slide, we will talk about that we only use the healthy control images. That means we do not have any COVID-19 patient images to train our model. This slide shows our proposed model called the weak variational autoencoder for localization and enhancement, the WVAL. is used to address the challenge. And our framework includes two components. We first have a model called the WVAE model that can help localize the anomaly. And then we enhance it to can carry out the supervised segmentation tasks. And this result was reported by Felix Ward. This slide shows the anomaly localization results. And we can see we have in total 3 COVID-19 infections, and we choose 2 healthy controls. And remember, the model is trained only from the healthy controls. And here you can see the first column is a pre-processed CT image. And we have from the Z1 to the Z4, which is the element-wise post hoc attention maps. And those attention maps is generated from our latent distributions, ZI. And the definition of ZI you can find from our publication. And the sixth column is showed the aggregated map. And the seventh column shows the segmentation result. And the last column is the ground truth. In this slide, we will show how to develop and deploy the cloud-based apps. So first, you need to buy the Microsoft Azure or the Amazon Web Services, the space. In the bottom left, you can see a schematic of how the AWS cloud can be used as a remote web server. There are too many technical things like the Amazon EC2, Amazon Simple Storage Service S3, and Amazon Workspaces. And the details can be found online. Then you need to run the web app server on the remote Ubuntu machine. Here we choose the Ubuntu operating system. Then we come into the right side. You can see what we should do is that we simply upload the CTF to the remote server. And after that, the tablet client, the smartphone client, the PDA, laptop, and the PC client, they can get access and run the app. And the user can even upload his or her chest images, and the remote server will give the diagnosis results. Here we choose a web service. And this slide shows the layout of this web service. We can see on the top shows the address bar, and the KDML is the short name of our laboratory, the knowledge discovery and machine learning. And we have the menu. Yeah, the menu is because this is a prototype software. We only have 2 menus: help and debug. And on the left hand, you can see there are thumbnail galleries. And here on the right, you can see there's a button group. The first button is that you can import your custom images. So that means the users can just get access to this URL and upload his own images to the remote servers, and the remote servers will return the prediction, the diagnosis results. And the results will be shown here. There's a knob. You can see the knob will link to these 5 categories. The 5 categories are none. It means maybe no image. So it is a kind of like a 0 or like a reset position. And there are 4 categories: COVID-19, community-acquired pneumonia, secondary pulmonary tuberculosis, and the last one is the healthy controls. And particularly we have 4 gauges here. The 4 gauges, like the progress of select the best 2 pre-trained models. Because this is a bit time consuming, so we need a gauge to show the progress. And also we have 2 gauges are used to indicate the progress of the DenseNet and ResNet. And finally, the other gauge is to show the fill-in progresses. And we have 3 lamps here. The 3 lamps are just used to indicate whether step 1 or step 2 or step 3, they are finished or not. So next slide, we will run this web web app service and to check how it works. So now we can have a look of how this will be run. First, I will click, yeah, okay, now it runs. And you can see here, this shows the names of 4 categories. Yeah, and then you click the thumbnail images, and then on the middle it shows the zoomed in, the enlarged, the fine detailed image. And after you click the detect, you can see how this model are running. And particularly you can drag and drop your custom images, and then you can also click detect. And after the 4 gauges to run to the 100, and all the 3 lamps are switched on, and you can get the result. So now let's come to the summation of this talk. The attendees, they may ask which model is the best for COVID-19 recognition. The answer is a bit complicated. Let's first check this Geiger principle, which means garbage in, garbage out. The principle, it means the prediction nowadays, it will depend heavily on the quality of the data. So that means the quality of the data influence our AI models. And the second is what we call the free lunch theory. It says, suppose we have all the possible COVID-19 detection problems called the F. So here is the F. And we have like 2 AI algorithms, A1 and A2. And we can see here the green circle. The F1 is the set of the problems where A1 is better than A2. And the rest space, the F minus F1, shows where A2 is better than A1. So the low free lunch theorem tells us the average performance of any pair of the algorithm models across all the possible COVID-19 recognition problems is identical. So in a nutshell, what we should do is try to explore more algorithms and more models. Thanks for listening to my talk. Any student or lecturers, professors are welcome to visit our lab in the United Kingdom. In this slide, I also leave my 2 emails. Feel free to write to me. And also, if you have any questions, you can ask now.